In this section, we're going to follow up with what we just did with hypothesis testing, but now in the case where sigma is unknown. We talked about that a while ago, situation where the population standard deviation was unknown. In cases like that, we use something similar but different to the z-scores in the z-score table. The same applies to hypothesis testing. Instead of z being the basis for the calculations, we're going to look back on the t-distribution and the table for t. So the process we're going to go through is level of significance has to be identified. Then we need to determine the degrees of freedom. This was something specific when we had to use the t-distribution. So df n minus 1. Find the critical values using the t-table in the row with n minus 1 degrees of freedom. If the hypothesis test is one-tailed, we're going to use left-tailed, we'll use the one-tail alpha column with a negative sign. If it's right-tailed, we're going to use the one-tail alpha column with a positive sign. If it's two-tailed, we're going to use the two-tails alpha column with a negative and a positive sign. So it's actually kind of nice in a sense because the t-distribution has indications for one-tail and two-tail testing versus the z-score where we kind of had to go a step further. We had our critical values, but we had to use alpha to figure out the tails and then in between, and then we could get the critical values from the table. But here, for the most part, all we have to remember is, do we use positive or negative, or do we use both when we're setting this up? And the picture here shows in the left-tailed, the left side is where a negative number for the critical value would be. On the right tail, critical number would be positive, but for both two tails, we use both a negative and the positive on both sides. So we're going to go through some examples of this. Let's find the critical value for t sub c for a left-tailed test given that alpha is 0.05 and n is equal to 21. First things first, we'll find the degrees of freedom by doing n minus 1 equal to 20. And then we're going to look this up in the t-distribution table. Okay, so I've cut off the distribution table down to the degrees of freedom is 20. Now, since we're using a one-tailed test for left-tailed with alpha is 0.05, we can look that up straight away and go straight to the number in the table, 1.725. That's going to tell us our critical value, but we just need to make sure to know, do we need to make it positive or negative? Since it's left-tailed, we're going to use a negative for what's in the table, so that'd be negative 1.725. Okay, and so there we go. We say that our critical value is denoted by negative 1.725. Let's look at another example. Let's find the critical values, negative t and positive t for the two-tailed distribution given by alpha is 0.10 with n is equal to 26. So the degrees of freedom, we subtract one away to get 25. And in the t-distribution table, we go down to the degrees of freedom's 25, but now we're doing two-tailed distribution with 0.10 for alpha. And so that means our critical value is coming from 1.708. However, this is two-tailed, so we need to take it as both a negative and a positive. So we're going to use negative 1.708 and positive 1.708, meaning that our critical values would be those two numbers in this case. Now in the long run, we're going to do a calculation similar to what we did for z-scores to get the t-value, and then we can use that to help us figure out if we're in the rejection region or not in the rejection region to reject the null hypothesis. So they say the t-test for a mean mu is a statistical test for a population mean. The test statistic is the sample mean x bar. The standardized test statistic is t equals x bar minus mu over s divided by the square root of n, where the conditions are met of sample is random and the population is normally distributed, or n is greater than or equal to 30. Of course, we need to also use the degrees of freedom n minus 1. So let's look at this example here. It says a used car dealer says that the mean price for used cars sold in the last month is at least $21,000. You suspect this claim is incorrect and find a random sample of 14 used cars sold in the last 12 months that has a mean price of $19,189. The standard deviation of the sample is $2,950. Is there enough evidence to reject the dealer's claim at the significance level alpha equals 0.05? Assume the population is normally distributed. Let's set up our numbers here. So n is equal to 14, x bar is equal to 19,189, s, the sample standard deviation, is 2,950. Let's keep track of our alpha is 0.05. Our degrees of freedom, we'll need to calculate that for our t-distribution. And so we need to do n minus 1, so 14 minus 1 equal to 13. Again, we're using that now because we don't have the population standard deviation anyway. It's just all from the sample. Okay, our null hypothesis is the dealer's claim that we're trying to make a alternative to, which is that the mu average of the population is greater than or equal to $21,000, because they're claiming that they're selling them on average for at least this much. The alternative to this is that it's not, it's less than that, which is mu less than $21,000. Okay, so now we know what type of test we're using here. It's less than on the alternative, so that means it's left-tailed test. Okay, now we can look things up in the table. Okay, I looked it up in the table, and here's where we're at. We're down to degrees of freedom is 13. Our alpha, we can look that up here, but we're doing one-tailed since it's left-tail, so we're just doing one tail. So that leads us to this value here of 1.771. So since this is left-tailed, we're going to use the negative. So that means our critical value TC, T sub C, is negative 1.771. Okay, if you'd like to sketch it here, it's kind of a normal distribution like curve, bell curve. But our critical value is over here, negative 1.771. And so what we're going to do here is think of it on the left side, left-tailed. So now what we need to do is determine, does our t variable rest in the tail or not in the tail, rejection region or not. So next we're going to calculate t using the formula x bar minus mu all over s divided by the square root of n. So that would look like 19,189 minus 21,000, which is mu in this case, divided by 2,950 divided by the square root of 14. That gives us a value of negative 2.297. So now we look at our left tail, and does it rest in the left side? In this case it does. Since negative 2.297 is less than negative 1.771, we'd see it somewhere over in here somewhere, meaning it does sit in the rejection region. So we can say we're going to reject the null hypothesis H sub 0 for this reason. And our interpretation of it is there's enough evidence at the 5% level of significance, or the 0.05 level, to reject the claim that the mean price of the used cars in the last 12 months is at least $21,000. There's enough evidence from the sample to reject that and probably make the claim that the mean average is actually less than $21,000. One more example here where we're going to need to use the t-distribution. It says an industrial company claims that the mean pH level of the water in a nearby river is 6.8. We're going to randomly select 39 water samples and measure the pH of each. The sample mean and sample standard deviation are 6.7 and 0.35 respectively. Is there enough evidence to reject the company's claim at 0.05? So let's go through here and write down what we have. Sample size is 39. X bar is the mean of the sample, 6.7. S is the standard deviation, 0.35. Degrees of freedom would be 39 minus 1 or equal to 38. Our null hypothesis is their starting assumption that the pH level mu, the average of the mean level pH of the population is 6.8, whereas the alternative hypothesis being claimed here is that it's not equal to 6.8. So do we have what kind of hypothesis test here? Since it's not equal to, it's again what we call a two-tailed hypothesis test. And so what we're going to do now is look up our information in the table. Alpha and degrees of freedom are the two numbers we need. So what we're going to have here is we're doing a two-tailed test, so let's underline that. Degrees of freedom 38, alpha is 0.05. So our critical numbers are coming from this 2.024. Since it's two-tailed, we're going to use both negative and positive values for the critical values here. So we need to use negative 2.024 and positive 2.024. So the gist of it here is these are our locations that determine where our rejection regions will be. Two-tailed test means we need to highlight both sides, both tails, and then check our value for t using the formula. T is equal to 6.7 minus 6.8 divided by 0.35 divided by the square root of 39. Comes out to be approximately negative 1.784. We then look at our rejection regions here, where does this negative 1.784 fall inside the rejection region or not? Well, visually we can confirm that it's going to actually be somewhere here in the middle. It's above the critical number. So it's actually not inside the rejection region. So in that case, we can think of it as the value for t sits in between the two critical values we have here. We don't have enough evidence to reject the null hypothesis. So basically what that means is there's not enough evidence to reject the claim that the pH level is 6.8. Even though we got a sample that may be less than 6.8, it's not significant enough either by size or comparatively to the claimed mean for the null hypothesis. It's not different enough to have enough evidence to support the alternative hypothesis.